Let's begin with a very simple question. So let's say you're in a laboratory, right? And you're given an input voltage, say some V in, and the input voltage source could have a lot of internal resistance. Okay, and what you're told is that there is a load resistor RL like this, and you're in a lab. So you are given say a variable voltage source, some kind of box on which there is a knob, right? You can vary. So this is a variable voltage source, is some kind of box which you can turn a knob and control the voltage, correct? And and what you are told to do, the task that you are asked to accomplish is make sure that the voltage VO across RL, and by the way RL is unknown, we just know it is there, but you do not know the exact value of the load resistance, is say I do not know, say 4 times VA. All right. So, let us think of ways in which we can make this happen, right? And you are in a lab, so you have access to, I do not know, perhaps voltmeters, ammeters, any measuring instruments that you might want are there at your disposal. So, the question is, how can we accomplish this task? What can we do? What all can we do? Okay. Okay. So, so one way of doing this is to basically say is measure V in with a voltmeter, okay, and basically and then what do you call set the voltage source to 4 V in, and then connect RL across the voltage source. All right, seems like a reasonable thing to do. Now, let us say let us say the voltage source, the variable voltage source is not ideal, in the sense that there is a small, remember that no voltage source in the world is ideal. So, let us say there is some small output resistance for this voltage source, correct. So, in other words, if there was no resistance loading the voltage source, then you set 4 V in on the dial and the output across the voltage source is 4 V in. But the moment you connect R in RL to the voltage source, the voltage will. So, you thought you had 4 V in, you made the measurement and then you set this to 4 V in, and you have this output resistance of the variable voltage source. And then of course, when you measure the voltage across the voltage source, it is 4 times V in, but the moment you connect this unknown RL, right, what happens to the voltage across RL? The voltage is no longer 4 times V in, it is going to be 4 times V in. So, if this is V out is actually 4 V in times RL by RL plus R out, and RL is unknown, and therefore, basically the output voltage is not guaranteed to be 4 times V. All right. Okay. So, now can we come up with a better approach than this? Can we think of another way of doing the same thing? I don't know, don't come to op amps as yet. Conceptually, what are we trying to do? What can we do? Okay, so okay, all right. So the second approach is well, two is okay. So we have our variable voltage source here. Perhaps it's got some output resistance which is say yet unknown. This is connected to the unknown load, all right, and this is V out. We know that V out must be V out must be 4 V in, no matter what RL is, correct. So, what do you do? Well, one way to do it, as he suggested, is to say, well, you connect a voltmeter here. This is our voltmeter. Right, the voltmeter is just a dabba, right, which can measure voltage. Recall what is the impedance of the voltmeter? What is the resistance of a voltmeter, of an ideal voltmeter? Right. So, remember the resistance presented by an ideal voltmeter is infinite. Okay, why did I remind you of that fact? Because you want to make sure that whatever you use to go, you use to measure the voltage V out should not go and change V out, correct. If the voltmeter was not ideal in the sense that the voltmeter had some resistance which was not infinite, the moment you connect it to that V out node, what will happen? Some current will flow through the voltmeter and change the voltage that you are trying to measure, and thereby you make a mistake in what you are measuring, correct. Fortunately, because the resistance of an ideal voltmeter is infinite, the act of connecting it to that node V out is not going to change the reading. Is that clear? All right. So, now the suggestion is that we know that we want V out to be 4 times V in, right. So, what as per his suggestion, what I am doing is where I connect the voltmeter across the resistor RL, unless it is your lucky day, a fat chance that the voltmeter is going to exactly read 4 times V in, correct. So, what is the suggestion? Therefore, what are we supposed to do? Compare. What do we want at the output? We want 4 V in. So, we must compare the output with yeah, so compare V out with 4 V in, all right. If V out is less than 4 V in, what does it mean? It means obviously that the output is not as large as it should be and V out must be increased. So, we wanted to say I will turn the knob in the clockwise direction to increase means the output is too small and therefore, must increase V out. Correct? All right. Now, on the other hand, if V out is greater than 4 V in, what does it mean? It means that the output is too small, is too large, and therefore, must decrease V out. All right. So, so basically once you are done with this process, eventually what will happen? What will the output voltage be? The output will be exactly equal to 4 times V in, and remember we have no knowledge still of RL or RO, the output resistance of the voltage source, correct. So, this basically I mean what processes have we used? We are comparing an output against a desired output and using the difference to go and tweak the output voltage in the right direction, right. So, this is an example of feedback, correct. But there is still a problem with this approach, and what is that? Well, what is that? Well, the problem is that where are we going to get 4 times V in, right? We are trying to generate 4 times V in, and now you are telling me go and get me another 4 times V in, so that I can compare it with 4 times V in, right. So, so can somebody think of a smarter way of doing this? We are almost there. Excellent, right. So, basically the approach which basically does not need you to generate have 4 V in to compare is to basically is the third approach, which does not have that disadvantage. So, basically what do you do? Well, you have the input voltage. Let me do that on a separate page. You have the input voltage, you have this variable voltage source, this variable voltage source has some unknown output resistance, okay, and this is going into some load which is unknown, all right. So, compare V out with, we want, remember what do we want? We want V out to be equal to 4 V in. Earlier we said compare V out with 4 V in and tweak V out in the right direction. Evidently this is problematic because we cannot get 4 V in if we had 4 V in, right. basically you know we would not be discussing this in the first place, right. So, so that is a problem. So, instead of comparing V out with 4 V in, it is equivalent to compare V out by 4 with V in. Okay. So, is it easier to generate 4 times V in V out or generate V out by 4? Why is it easier to generate V out by 4? Yeah, well, V out by 4 is easily generated, for example, by using a resistor divider. Correct? All right. So, so what do we do? Therefore, we basically say, okay, I am going to generate V out by 4, and what am I going to do? I am going to put in a resistor divider as was suggested. So, let us call this R. If I want V out by 4, what should this resistance be? That should be 3R. So, this voltage is going to be V out by 4. Correct? And where do we put our voltmeter now? That voltmeter box is going to get connected between the input and that node, right. So, that is this is the voltmeter, and again remember the voltmeter does not draw any current. So, connecting it between those two nodes is not going to disturb the voltage across those two nodes, correct. Now, if and what is the voltage, therefore, what is the voltage across the voltmeter? The voltmeter reads the difference between the two nodes, which is V in minus V out by 4, correct. So, comparing V out by 4 with V in is the same as comparing V in minus V out by 4 with 0, correct. So, basically so now how do we rephrase what we want to do? We look at the voltmeter reading. If the voltmeter reads more than 0, in other words, if V in is greater than V out by 4, what does it mean? It means that V out is too small. What must I do? I must increase V out by turning the knob in the right direction. Is that clear? And on the other hand, if V in is less than V out by 4, what does it mean? It means that V out is too large, and what must I do? Must decrease V out. All right. Okay. And this whole process basically if V in is greater than V out, it is equivalent to saying that V in minus V out by 4 is greater than 0. This is equivalent to saying V in minus V out by 4 is less than 0. Is that clear? And so, this whole process where you compare the output with the desired output, right, and vary vary something so that the difference between the actual output and the desired output is 0. This is an example of feedback. It turns out that it is actually negative feedback. We will come to why it is called negative feedback going forward. So, but this is what is called, this is negative feedback. All right. And let us take a step back and see what we have achieved. We remember that we do not know what R out is, we do not know what RL is. Okay. Regardless of the fact that we do not have this information, if we follow this process, right, we will still be able to get to the output being exactly equal to 4 times the input. Does it make sense? All right. So, I mean, to give an analogy, right, it is like finding directions. Okay. So, of course, now we have Google Maps to let us say you want to go from, I do not know, from this building to Gajendra Circle, right. So, you plop Gajendra Circle into your Google Maps, and Google Maps will say, well, you walk out of this room and then make a left and walk exactly 62 feet, and then you make a right, and then walk 10 feet, you will come to a staircase, go down by 30 feet and you will hit the ground floor, make a right, and walk I do not know 0.2 miles, and then you will be at GC, right. This is an example of an open loop system, right, where the final accuracy is dependent on basically the accuracy of these numbers, right. So, Google Maps tells you go walk 62 feet and make a right, all right. Now, maybe somebody was entering data made a mistake, and the 62 actually I mean by mistake the 62 became 92 feet, right, and you were simply a robot who was just following orders, right. You overshoot, and then you make a right and you will jump off the corridor and fall down, correct. Okay. And likewise, instead of 0.2 miles to GC, if it says if it became 2 miles by mistake and somebody missed a decimal point, then you will be at the in gate, not at GC, correct. So, the accuracy or the efficacy of an open loop system is predicated on how accurately each of those numbers are, correct. Okay. Another example I would like to give is, let us say you are eating food in the mess, okay, and you have a spoon in your hand, there is food in your plate, and then you put your hand to the you put your spoon in the food and then take it to your mouth, and that is how you eat, okay. But if you had to tell a machine to do it, what would you have to say? Well, you apply so many newtons of force on the spoon, and then you push up with this angle and this thing for so long, and then do this, and then the food goes into the mouth, right. But you are never doing all this consciously. What are you doing? You are always in the first case where you are giving directions. What do? Right. The natural way of giving directions is, if a friend wants to go to GC, you basically say you turn left, then take the first right, and then after that take the first right, you will get to a stairwell, you go all the way to the ground floor, make a left, you will get out of the building, make a right and keep walking, and you will see a big circle, that is GC, correct. Now, there is no 62 feet, make a right, because what are you saying? Go and make the first right. So, what is the person going to do? Is going to keep watching, right. The moment he finds he or she is going to keep walking as long as their current position does not coincide with the first right, all right. Okay. So, we have never told him or her how far the first right is, we just said keep walking. The moment you find your first right, you can make a right, all right. And likewise, you get out of the building and then keep walking, make a right, keep walking, the first big circle you see will be GC. Now, you not exactly told them how much distance to go, right, but so at every time subconsciously what the person is doing is looking around, looking for a circle, and so if he or she does not find a circle, they keep walking in that direction. So, basically what you do is dependent on the error between where you want to be and where you actually are, right. And likewise with food, you are never doing all this math and applying so many newtons of force on your spoon and doing all this stuff, and automatically does your hand seems to do the right thing, right. Why? Because your eyes are basically looking at the difference in position between your spoon and your mouth, and applying whatever force is is needed to be applied, so that the food in the spoon comes into your mouth. If you do not believe me, try shutting off your eyes and then taking a spoon and feeding your friend on the side, right. You obviously will not be able to do it, because you are most likely going to spill sambar on the shirt, because you do not know where his mouth is, you do not know where your hand is, okay, and you do not know where the sambar is either, right. So, basically you understand. So, basically, so if you want any system to be robust, right, like in this particular example that we are talking about, we have no clue what RL is, we have no clue what R out of the voltage source itself is, right. But in spite of that, by simply measuring the difference between the actual output and the desired output, the actual output is we have taken, instead of for practical reasons, we are measuring the difference between a fraction of the actual output and the input, and using that error, which is V in minus V out by 4 in this example, to go and tweak the voltage source dial setting in the right direction, so as to make the output exactly equal to 4 times V, right. Does make sense? Okay. Now, of course, every time you want 4 times V in, you can't send a person and a voltmeter and say keep measuring V out by 4 and V in and then tweak that stuff, right. But basically the understanding is anything that you can describe clearly using words can also be done using an electronic circuit, right. So, let us stare at what exactly this is doing. This is a variable voltage source, correct, but this variable voltage source is controlled by what source? What are we using to go and set that variable voltage source? We are basically using the difference between V out and V out by 4, that difference between those two nodes is used to go and control that variable voltage source. So, in other words, this is not merely a voltage source, it is a voltage controlled voltage source, because that voltage the voltage source is controlled by the difference between V in and V out by 4.